So we're gonna Alex give us the last talk. It's been absolutely fantastic to have him back here this week. I haven't seen Alex in a while. It's impossible to overstate how important he's been to my own intellectual life. I could go on and on about this, but suffice to say that for the past 10 years or so, every time I run into some magical, amazing object, it turns out that Alex has been there before and ready to tell me something. So I'm going to pay a lot of attention. So take it away, Alex.
Okay, so thank you very much for the introduction and for the invitation to this wonderful event and for the last talk. So this talk is based on a joint work with Thomas Lamb. So sometimes we wrote a paper called Poly-positroids, but actually there's another paper which is not out here. It's called Poly-positroid 2, and that will be like the main focus of this talk. So if you already heard a talk of me, I was given several talks many years ago with the same title. So if you already heard it, so don't worry. So today will be a brand new talk. So it's yeah, that's what I wanted. Yeah, poly-positroids. Okay, and one disclaimer that I'm not going to talk about physics at all. So that's will be purely mathematical talk, and I'm going to use. So my talk will be. So I'm not very elementary. So I'm not going to talk about some esoteric objects like m equals to 6 amplidihedron and so on. So everything will be completely accessible to elementary school students, the first graders. So I'm going to just use some elementary combinatorics, maybe a little bit of linear algebra, but kind of very simple linear algebra, like how to add vectors. So that's all you need to know to understand this talk. But so there's definitely some physics related to this stuff that I'm going to discuss. So it's going to be a homework for you to actually find out how all these objects that I'm going to talk about are called in physics. Okay, so let me give a more expanded couple of keywords. 3 keywords. So poly-positroids. I'm going to explain you what poly-positroids are. Another important objects that are going to appear are called asymmetric metric spaces. And another keyword is tropical positive Grassmannian. So we are going to talk about these 3 things. And in the beginning of the talk, I'm going to discuss 4 different objects. First objects are going to be matroids. Then we'll talk about some special class of matroids, which are called positroids. Then we are going to talk about generalizations of matroids, which are called polymatroids. And then we're going to talk about poly-positroids, which are generalization of positroids and special class of polymatroids. So we had this commutative diagram with 4 elements, and we will discuss each of these 4 objects in 4 steps. So it will be 4 by 4. That's my plan for the beginning of the talk. So let me start with matroids. And I'm sorry, so here there are a lot of specialists who are kind of know everything about matroids. Actually, like main specialists, I guess, on these are here. So it will be completely trivial to you, so you will know all these things. But let me briefly go over the question. What is a matroid? So first, first step or even 0th step, which is not a definition of matroids, but it's a kind of motivation, inspiration, where these objects are coming from. It's a configuration of vectors. So imagine you have n vectors in some k-dimensional space over some field, and we don't really care about kind of these vectors themselves, but more about linear dependencies between vectors. Whether vector 1 is linearly can be expressed as a linear combination of v2 and v3. So these kind of questions, this data, that will be a matroid. And so in a more concrete way, this collection of vectors can be represented by k by n m matrix. So k by m matrix represents some matroids. This is not a definition of matroids. This is definition of realizable matroids. There are some matroids which are not coming from vectors, but kind of that's like the idea. So we want to understand dependencies between vectors. Okay, like just to make physicists happy, again, I said I'm not going to talk about physics, but if you're a physicist, so n here is the number of particles, k is the helicity. I think that's, but that's, okay. Okay, maybe that's not true. So everything I'm going to say about physics is going to be very kind of like, basically, it's going to be pseudo-physics. So I'm not going to. Okay. Anyway, so think about K-band metrics. Now, more concretely, these things can be described in several different ways. There are many different cryptomorphic ways to define a matroid. And let me mention 3 of them, which are going to be the most relevant for us. One, like the most common way how people define matroids is by giving a set of bases. It's a set of k-dimensional subset in n-element set. So basically, whenever k of these vectors form a linear basis of our space, that's the base of matroid. And there is some exchange axiom. There's axiomatic description, and you know very well this, so I'm not going to go into detail. So, but that's set of bases. Another way to define matroids is by giving a rank function. So that's going to be a function from all subsets of our base set. So there are like 2 to the n subsets, 2 integer numbers. So that takes some subset of these vectors and calculates the dimension of the span of these vectors. So that's going to be certain function on 2 to the n elements, which is called rank function. And again, there is some conditions that it's not any function. There are some special conditions that describe these things. Finally, another way to think about matroids is by talking about matroid polytopes. So matroid polytopes is going to be some polytope in Rn. So it's going to be for any base. It's a subset. You can represent it by a binary vector, like 0, 1, 0, 1, and so on. And you take the convex hull of these vectors, you get some nice polytope. And let me maybe briefly mention that for number 3, there is actually, again, very nice characterization of these polytopes, which is due to Gelfand, Goretzky, McPherson, Serganova. So polytope is a matroid polytope if and only if all vectors, all vertices are binary vectors. That's kind of immediately from the definition. But important thing is that all edges are parallel to EI minus EJ. So increase one coordinate by 1, you decrease another coordinate by 1. And this kind of all edges are directed like this. So this, I'm going to call this EI minus EJ's roots. So all edges are parallel to roots. Okay, so that's simple, like 1, 2, 3. 0, 0, 1, 2, 3. So then we can wonder, if somebody gives you a matroid, what is this? Suppose it is a realizable matroid. What is the space of matrices A that realize this matroid? What is the realization space? Matroid, and there is some result, which is called Mnev universality theorem, that says that basically the realization space of matroid can be arbitrarily complicated, as crazy as you can imagine in algebraic geometry. So I'm not going to formulate it precisely, but basically realization spaces of matroids in general are wild. And I remember I was actually here in Princeton. Then I was a graduate student, and I was talking to Voevodsky, and he explained, we discussed Mnev theorem, and he explained me that actually Mnev theorem is a trivial statement. It's not something very hard to calculate. He explained it, and it was really known to ancient Greeks. So ancient Greeks already knew Mnev theorem. And so why? So ancient Greeks didn't do any algebra. They didn't do any algebraic geometry, because for simple reason that these things were not invented at that time. But the only thing that they did, they just draw lines, triangles on the plane, things like this. And like if you are, in an elementary school student, like first grader, you can draw lines and triangles. You can put one line segment of length n next to line segment of length b. You get a plus b, right? So you can, even if you don't know anything about numbers, you can add numbers by putting. You can also multiply numbers. If you draw 2 homothetic triangles, let's say this side is like our unit of length. This is a, this is b. then this should be A plus B. So you can multiply numbers by drawing lines on the plane. And if you know how to multiply, add and multiply can express any algebraic operation. You can express any polynomial by some configurations of lines on the plane. Or you can express any system of polynomials. So basically, you can convert any problem in algebraic geometry into some configurations of lines on the planes. So, and we know like algebraic geometries can be pretty complicated. So basically, these realization spaces of matroids are like as hard as anything you can imagine in algebraic geometry. Okay. Now, is it like really hopeless? Now, should we give up and just stop thinking about matroids? Okay, so maybe if you see some complicated objects, maybe instead of kind of thinking about all matroids, we can try to single out one especially nice class of matroids, which is already interesting and complicated enough to, do hard problems like calculate scattering amplitudes and things like this, but kind of complicated in a kind of manageable way, not crazy complicated as algebra, as arbitrary matroids, but in a kind of manageably complicated, so that you can explain everything in simple chemical objects. And there is actually a class of matroids like this, which is called positroids. Okay, and I have to do heavy lifting for this blackboard. Okay, positroids. So basically, simple definition, like definition number 0. Now it is a definition. It's not like a motivation definition. Positroids are exactly matroids. They're all realizable by metrics such that all maximal minors of these metrics are non-negative. Okay, and then we can like do these 3 steps, 1, 2, and 3. We can characterize them by giving some conditions on basis. So there are some additional conditions in addition to exchange axiom. You can characterize them by giving conditions on functions, kind of describing rank functions. Like for those of you who know, I think here there are a lot of people know this is going to be, number 2 is going to be decorated permutations. So they're like, and you can characterize matroid polytopes also. It's going to be some class of positroid polytopes. You can characterize them by some simple conditions. So I'm not going to do it right now because, first of all, many people already know how to do it. Secondly, that we're going in a moment we're going to do it in a more general setting. So I'm going to do 1, 2, 3 in a more general thing. So now let's move on. So like another approach, if you see some crazy and complicated objects, maybe instead of, and you cannot say much about it in general, maybe you can even try to generalize it, make it even more complicated. And so that might provide you some additional hints. And then there is a generalization of matroids, which is called polymatroids. So again, let me do kind of not a definition, but a motivation for polymatroids instead of configuration of vectors. And really, we are caring not about vectors, but about spans of these vectors by one-dimensional subspaces. We can think about configuration of arbitrary subspaces in some vector space. So pick some subspaces, and that will be a motivation. Again, that's not all. Polymatroids are coming from configurations of subspaces that these are going to be realizable polymatroids. But you can define them. Again, there are many different ways to define them. You can define them by extending this notion of basis. Now, bases are no longer be subsets, but multisets. So the same index might appear many times. And the other way to think about them as certain integer vectors. So this will be certain collections of integer vectors. All of them will lie in the same hyperplane, sum of all coordinates equals k. And they should satisfy some generalization of exchange axiom. And this exchange axiom is called M convexity. So they're called M convex sets. So what is M convexity? Let me briefly tell you what it is. Again, if you know exchange axiom, you should know how to how it's related. So for any 2 points, like integer points A and B in a polymatroid, let me call this things also M. So for any two integer points, and I remember sum of all coordinates in A equals sum of all coordinates in B. So if there exists an index I such that AI is greater than BI, for any index such that AI is greater than Y, there exists J such that AJ is less than BJ, so that you can start from point A, add vector EJ minus EI, or simultaneously start from point BJ and add vector EI minus EJ, and you are still going to be inside your polymatroid. So you kind of, these are kind of discrete notion of convexity. They're convex in this kind of discrete sense. If you have 2 points, then you can kind of move closer to each other. You cannot literally move along this line segment and connect them, but you can try to do the best thing that you can imagine. Just move them slightly by this EI minus EJ towards each other. So that is the M convexity. Next, we can, okay, so let me maybe move here. So how to do number 2? So number 2 is the notion of rank functions. So how to characterize them in terms of rank functions? Yeah. Why is a polymatroid?
Why doesn't the polymatroid just sit inside this bigger matroid? Isn't all the information of the polymatroid inside?
So the information. So question is, why is it going to be convex in this sense, or?
No, it's a much dumber question. Doesn't the polymatroid sit inside a bigger matroid?
Yeah, it is. Yeah, you can actually think about this in this way, right? So, but in a higher, like for bigger M. So in a high dimensional space, you can think about this as a projection of some high dimensional matroids. Yeah, that's definitely true. So, but another way to think about them is in terms of rank functions. So now rank functions, again, it's going to be functions on subsets. That satisfies so the important condition, there is like one condition on this rank function. And this important condition is called submodular condition. Submodular function. And that means like rho of I plus, for any two subsets, rho of I plus rho of J is greater than or equal than rho of I union J plus rho of I intersect J. So that's going to be like the central notion for us. So this is submodular condition. And maybe let me say, just for concreteness, for empty set, rho equals 0. And then it will be convenient for us to assume that rho of the whole set is also 0. Now, it may sound a little crazy because rho of the whole set should be the whole, yeah. So, and again, like in this example, what is the rank function is you take sum of this subset of these vector spaces, take their span, and that's the dimensional span of some subset of these vector spaces. So clearly, like, vector spaces satisfy this, if these ij are subspaces, then that's some basic inequality for dimensions of subspaces. Now, this second condition looks a little crazy because rho of n should be k, should be a helicity or not helicity, but should be some non-zero number. But actually, what we can do, there are some trivial operations you can do. These are called submodular function, but if you put equality here, then they are called modular function. And you can always add a modular function to a submodular function. Modular functions are just some simple linear space. So you can, by kind of adding some sufficient appropriate modular functions, you can kind of shift this hyperplane anywhere. So basically, once we go from matroids to polymatroids, we can just assume that k equals 0. So there's like basically all k's become equal. Assume that k equals 0. So from now on, I'm going to assume that k is 0. Just for, it will be slightly more convenient for us. And its rank function is no longer positive. That's slightly different than the usual definition of polymatroids, because in this classical definition, they require that rank function is positive, monotone, and so on. So we just skip in these conditions. It's no longer positive, and it's going to be important for us. But just this condition, just this submodal condition. Finally, number 3 can describe a class of polydopes, which are called generalized permutahedra. Generalized permutahedra. So they're going to be polydopes. Now they live in this subspace. Sum of all coordinates equals 0, well, equals k, but now k is 0 in Rn, well, which is isomorphic to Rn minus 1, actually. It's a hyperplane. And the only condition is that all edges are parallel to the roots, ei minus ej. Okay, so we kind of skip this condition that all vertices are binary vectors, because that's really not important condition. Just skip this condition. And that will be exactly class of generalized permutahedra, like one way to define them. So they're going to be like for n equals 3, they're going to be 2-dimensional polydopes. That's kind of generically look like hexagons. Okay, so that will be so. And actually, all these things, 1, 2, and 3, are equivalent to each other. Okay, now let me go to poly-positroids. Yes?
Yeah, the parallel to ei minus ej. Is it equivalent to say that the facet, the normals to the polydopes are binary vectors?
Facets? No, it's not fine. No. No, that's not true. But they are also binary vectors. It's true, but that's like a theorem. In one direction it follows, but it's not true in general. So now let me define polymatroids. So let me go back to where I should. Okay, let me do it here. So the polypositroids, that's the class that we are interested in. So I'm going to kind of add some extra conditions to polymatroids, and I'm going to start with 0. So a polypositroid is a matroids. Oh, polymatroids, sorry, polymatroids. Realizable. So polymatroids realizable by configuration of subspaces v1.vn such that there exists a matrix A, k by bigger n matrix, which has all non-negative maximum minors, such that you can kind of block this matrix A into blocks, kind of vertically, and kind of into consecutive blocks. And this first block will span vector space V1, second set of columns will span V2, and so on. Okay. Okay, so it's kind of block matrix. So notice that, well, maybe I should said it earlier than we discussed polymatroids. We cannot, like then we are going from matroids to polymatroids, we cannot get something for nothing. So we need to make a sacrifice. Then we talk about polypositroids. The sacrifice, our sacrificial lamb, is SN symmetry. So positroids are not, the notion of polypositroids is not invariant under all permutations of the ground set, but it's invariant under cyclic permutations. So, and somehow we can combine only consecutive blocks together. So it's not the definition of polypositroids in our original paper, I'm going to give you another definition, but that's kind of the definition that I like. I can give you, but there is something slightly unsatisfactory about this definition. So what's unsatisfactory about this definition is this existence of matrix A. So it's like, in order to test this, like if somebody gives you a bunch of subspaces, how do we test that this condition holds? So you need to pick a basis in each of these subspaces that would make this matrix positive. That's actually kind of infinite verification. It's like a continuum, many ways to do it. So there is actually, this definition may be theoretically interesting, but like from practical point of view, it's useless. So kind of problem, maybe interesting problem that I'm not going to discuss now, is actually how to check this condition. Like if somebody gives you a bunch of subspaces, how do we actually check that we can find basis in all of these subspaces such that all maximum minors become positive? That might be kind of interesting problem, which I'm not going to address. But let me mention one good thing is that there is a special class of polypositroids. So suppose that all the i's are even dimensional. So then actually this notion is asymmetric. So if it happens, we have like some special class of polypositroids where all the i's are even dimensional, then actually by this definition, you can take any permutation of these blocks. And I mean, this notion of positive minors is not going to change. So there is like a special class of polypositroids, unlike usual positroids, which has this S-on symmetry. Okay, but let me move on. Let me describe these polypositroids in terms of basis. So we already know how to do number one. Number one. So we have this notion of M. So we have some subspace, let me call it maybe M, in the integer lattice. It lives in a hyperplane. It should be M convex. So we have this, notion for any A and B. We can kind of slightly move towards A and B by vector EI minus EJ and EJ minus EI. We have this notion of M convexity. But I should mention that this is kind of some discrete convexity, but that's not the only notion of discrete convexity. There is another concept of discrete convexity, which we can like to call sorted convexity. Sorted convexity. So there's another thing that you like, that we would expect from a convex set. If you have 2 points, A and B, you can jump from these 2 points to the midpoint of this line segment. It's A plus B over 2. Okay, so if A and B belongs to M, that implies that A plus B over 2 also belongs to M. Well, if A plus B over 2 is an integer number, but it may not be integer because we divide it by 2. It may not be an integer vector. It might involve some half-integer coordinates. So it means that if it's not an integer, we want to kind of do the best thing that we can imagine, try to find the nearest integer. Kind of try to round this A plus B over 2 to the nearest integer. Let me put it like braces here. That's not literally A plus 2, but we need to, if it has like 1/2, we want to replace it either by 0 or by 1. And remember, we want to keep the sum equal. So it means that if you round some half integers up, then you should round some half integer down. And the way how we do it, we want to do it like most natural thing to do it in alternating way. You find all half integers, round the first of them up, round the next down, up, down, and so on. And that's what this notation that I use here, A plus B over 2. So we kind of find the closest kind of integer point to the midpoint of the line segment. So we kind of sort this, and this is called sorted convexity. So, and we want to impose both of these conditions. And that's actually exactly equivalent to, that's kind of the correct notion. So next thing that I want to do. Let me. Well, again, for we take this cyclic, so basically it depends on cyclic ordering of coordinates. This notion, unless this polypositroid is even, so it's not invariant under all permutations, it's cyclic ordering. So you just put your coordinates in cyclic order and just round up, down, like as you go around the cycle. So next thing is how do we describe them in terms of rank functions? And so they're going to be submodular functions. So it turns out that, there is like some, as you notice, instead of this notion, there's some kind of cyclicity about this definition. So, and it turns out I don't need to, in order to talk about polypositroids, we don't need to talk about all subsets. We only want to care about cyclic intervals. So it's going to be rank functions on cyclic intervals. So we have like rho that goes from some cyclic interval I plus 1, ... let me say j minus 1. And let me denote this Rij. So instead of indicating ranks of all subspaces, I want to indicate ranks of these cyclic intervals. So instead of 2 to the n array of numbers, we have n square array of numbers. And they should satisfy, but they should still satisfy submodular conditions. So let me write down the analog of that equation in this case. So the analog is the following. So whenever you have 4 indices on a cycle, I, j, k, l, arranged on the cycle, so you take rank of ik, ik. So you take this pair plus rank of jl plus this thing, that's exactly the submodular condition, r of I, rho of I plus rho of j, and it should be greater than or equal than ranks of these two things. It's greater than or equal, and r, the union of these two segments will be rijl plus rjk. That will be our key identity. And of course, like rii will be just 0. Okay, so we have this notion. And for example, I think Nima was kind of writing exactly the same inequality yesterday. Or so like in physics, this inequality somehow appears. That's exactly a description of its kind of arrays of numbers satisfying this axiom. So notice that this condition implies the triangle inequality. If you specialize j equals to k, you get the triangle inequality rij plus rjl is greater than ril. We have triangle inequalities. And if we specialize it even further, we can get even more trivial inequality rij plus rji is greater than 0. So notice I do allow ranks to be negative. That's going to be important for us. But I still want to, they should satisfy this, sum of these two opposite ranks should be non-negative. So that's notion of positroids. So notice that this set of inequalities is not the minimal. There are some redundancies here. Some of them follow from the others. If we want to write down the minimal set of inequalities, that's a little exercise to show that it's enough to impose only these inequalities, then j equals to I plus 1 and L equals to k plus 1. So we can have these inequalities for this diagram, like I plus 1, which appears in physics in many, like k plus 1. So that's, these inequalities will give us minimal set of inequalities. Okay, so we can describe the same data by writing down entries like mij, which is difference. So will be what it's this plus this minus this times this. So what is it? It's r. Okay, I'm kind of get confused here. Okay, so we can describe the same data by writing r I k plus r I plus 1. Sorry, r I j r I plus 1 j plus 1 minus r I j plus 1 minus r j plus 1 I. So define this other set of parameterization. Then what it happens that these mij inequality are just given by conditions. These mij's are greater or equal to 0. But now these mij's are not in the, so these RIGs are independent, linearly independent, but there are some relations between mij's. Otherwise, it would be too trivial. So the relations are that sum over all I mij equals to sum over all I prime, sorry, m I prime, sorry, sum over all k m ki. So I don't know if you, sorry for, but let me just say, you can think about these mij's as multiplicities, they're non-negative numbers, as multiplicities of edges of some directed graph. And the only condition is that for any vertex, in degree equals to the out degree. So like in equals to out, we call these balanced graphs. And these balanced graphs are literally, if you know the story about positive Grassmannian, they're literally generalization of the decorated permutations. Decorated permutation is a very special case of balanced graphs. If all is, yeah. Yeah, important thing is that mij is not, may not be, and usually it's not equal to mji. So, but there are two non-negative numbers, so it's a directed graph, but in degree, for any vertex, in degree equals to the out degree. So if all these in degrees and out degrees are 1, then we're back to the positroid case. If there's something bigger, then we get something more interesting. Okay. So finally, let me do number 3. So I'm going very slow. Instead of generalized permutahedra, we have more special condition is that poly-positroid polytopes, and that's actually how we define them in the first paper, poly-positroid polytopes. So we have this condition that all edges, that there should be generalized permutahedra, all edges are parallel to the roots, ei minus ej. And then we have to add another condition. Actually, kind of that looks like almost opposite, but we have to say condition on the facets. All facets are normal also to roots, but not exactly the roots, because like if you literally, you cannot find a polytope whose edges kind of normal to all facets other than, cube. I think it's impossible to find. So you need to kind of do a little twist. You have to replay, so we call it twisted roots. So what's a twisted root? Again, it's ei tilde minus ej tilde. So what is ei tilde? It's ei tilde is just the e1 plus e2 plus ... plus ei. That's kind of initial segment. And we are taking it kind of lives in the dual. So this polytope lives in the space all coordinates equals to 0. This facet normal should be live in a dual space. So it is in Rn modular vector 1, 1, 1, 1, 1. R. So we look at these twisted roots, which are also kind of linear isomorphic to roots, but given by some kind of simple linear transformation, and we require conditional edges on facets. So theorem that 0 is equivalent to 1, is equivalent to 2, is equivalent to 3. So all these 4 different ways to define polypositroids are equivalent. Okay, now I done the first quarter of my talk, and I used almost all my time. Yes?
Is there a polynomial that you associate to poly-positroid whose Newton polytope is the corresponding poly-positroid polytope?
Yeah, I mean, Yeah, I guess so, but let me think. I mean, there should be polynomials whose Newton polynomial, but yeah, maybe. I mean, let me maybe talk later. Okay, but let me move on to the kind of, this is new things. New things. So let me talk about asymmetric metric spaces. So what is this asymmetric metric space? So that is a certain space with a distance function. So for any 2 points, we have a distance, d of x and y, distance. And it satisfies what you want to expect from distance. Distance of x, y, triangle inequalities. From distance from y, z is greater or equal than distance from x to z. Okay, so that's kind of normal. And also distance from x to x is greater or equal to 0. So that's the only condition. Notice that I didn't write anything else. I didn't require that distance from x to y equals to distance from y to x. They actually might be kind of different. So it might sound a little wild, but actually I want to argue that actually makes a lot of sense, because in normal life, that's what happens about the distance. So in normal life, like if you ever drove in in a traffic, especially in places with a lot of one-way streets, like to go from one place to the other, it can be totally different than returning back. Notice that I didn't even write anything about saying that distance should be positive. It might actually be negative. That's fine with me. And actually, we do want to allow negative distance. But like from these inequalities, if you specialize x to y, there's one important corollary, is that distance from x to y plus distance from y to x is greater than 0. So I want to call it like no loopholes. So imagine, so like that, now I'm going to say something like really pseudo-physical, but I don't know. So like some thing that I have in mind is that, so imagine that you travel in a space shuttle to distant galaxy, to galaxy far, far away. Then actually I allow, like if it happens, I allow you to go back in time. So you can go back in time and see all events of the Star Wars. But if you want return back to the Earth, then you are not allowed to go in the past. So you can go to the past in the other place, but if you want to come back, actually we cannot come back like in time. So we have to move in future, but in the same point. But in some other point, we can be like back in time. So I'm calling it like no loopholes. We cannot have this travel around the world actually, but but travel back in time is allowed. You can actually see Star Wars like happening like in real life. Okay, so how all these things is related to? Like it looks like totally crazy thing, but let me actually try to. Okay. Oh, I shouldn't have erased this, but let me erase the other part because we need this inequality. So because that's okay. So now let's specialize to the case of a disk. Imagine that our space is a disk. With n marked points. We have disk, and we have points z1, z2, zn. Right? So we have these points on the disk. And then we can, we only care about these marked points. We only care about distances between these marked points. So let me call it dij equals to distance from zi to zj. So this distance satisfies the triangle inequality. But actually, there is a little bit more than it satisfies. It's not just the triangle inequality, but imagine that you calculate this distance, right? And it's kind of, you can find a geodesic, like from I to J. Suppose you have like I, J, K, L. You find distance from I to K, and then you find this distance from J to L. Then notice that these two geodesics should intersect. That means that this distance should be actually, using triangle inequality on a disk, we get exactly these inequalities. K plus DJL greater or equal than DIL plus DJK. We get exactly these inequalities. So this distance function satisfies kind of, so any asymmetric metric space on a disk with n marked points literally gives rise to a polypositroid. But we want to do something discrete. So that's something, smooth, continuous, some kind of general thing. Let us actually want to get combinatorics. So where do we get combinatorics from? And I have, well, I don't know how much time I have, but because that's like even, I'm close to half of the talk now, but okay, yeah, I have to travel back in time. Yeah, but let's actually draw all our marked points, and we really only care about these distances between marked points. Let me actually draw all geodesics. For any pair of points, I'm going to draw all these possible geodesics. So we'll get, some kind of graph like this, So we get some directed graph. Now, so these some edge weights. So there will be some edge weights on every edge. So we get a directed graph with edge weights, and what's the Dij? Dij is going to be the minimum over all paths P from Zi to Zj of what? Of sum of all edge weights. Now, if you look at this expression, you can actually, if you know anything about positive Grassmannian, you can immediately recognize this expression as the tropicalization of the boundary measurements for the positive Grassmannian. So, and that means that it's tropical, so we can do all combinatorics that like all kind of moves, square moves, and so on. We can reduce this graph to trivalent graph with black and white vertices. Again, I don't want to do it, but basically all combinatorics about Plebbe graphs just pops out from these asymmetric metric spaces. And so we'll, but there are some little, tiny new features. Like there are some new phenomena that you will observe in this tropicalization. So let me give one example. What? No, weights are not, but there are some, the weights can be negative, as I said, and we do need to allow them to be negative to make everything work. Right, but these are kind of tropical weights. So basically, we get what we call tropical Plebbe graphs. So the weights are basically, which are exactly the same thing as usual Plebbe graphs, but the weights are tropicals. So let me give you one example of a tropical Plebbe graph. So that's like the only, maybe many of you know this graph very well. And we have edge directions. Basically, we get all combinatorics of these tropical Plebbe graphs, 1, 2, 3, 4. And let me put this like A, B, C, D. That may or may not be negative numbers. So then the tropical boundary measurements, Mij, is just what? There are two ways to go from 1 to 4. Like, sorry, M14. Like, let me write distance from 1 to 4. That's the tropical measurement. D14 equals, there is a way, it's minimum of two things. Minimum of B, and also you can go like A, C, D. A plus C plus D. So notice that if this, if B is greater than A plus C plus D, then we should travel like this. Every time when you travel, you will never use HB. So it means that in this case, in the tropical Playback graphs, in this case, this graph is not reduced. So this graph will not be a reduced graph. And somehow, if we want to define reduced Playback graphs, we have to impose this condition, this additional restriction. So this, in reduced graphs, these weights are no longer be just arbitrary weights, but they satisfy some inequalities. So reduced, if B is less than or equal to A plus C plus D. So it means that in a reduced Playback graphs, all edge weights will satisfy some addition. So every reduced Playback graph will come with some cone of inequalities. In this case, that's this inequality. And that's kind of, again, looks a little bit similar to pictures that Nima was drawing about this, what is it, cosmohedron? So anyway, so the rigorous way to define it is that actually in reduced Playback graphs, for any pair of boundary edges, we need to fix one particular geodesic. And we want to require that any edge appears in at least one geodesic. And inequalities are that the path along this geodesic, the sum of along this geodesic, is less or equal than sum over any other path from I to J. So that's exactly the cone, the objects. These are Playback graphs with choice of geodesics, and all edges appear in any geodesic and reduced graphs. Yep.
Does that guarantee that the inequalities are satisfied for all the other representations of the top cell? Or is there a different set of inequalities?
So there might be different sets. So like every time when you do square move, you have to transform this. Yeah. Yeah. Yeah.
The usual relationship to the axis graphs, right?
Yeah. So there's a usual relation, but like in a Playback graph, so basically then you fix this additional information. We are kind of picking one, so they're given by like minimum and maximum in general, but we are kind of picking 1 degree of linearity. So this kind of choice of geodesic tells us one kind of piece of linearity of this object. And this object is, well, yeah, Lauren, yeah. Yeah, probably can formulate it, but I want to be elementary. I don't want to talk about Poisson spheres, just numbers. Yeah, but that probably can be formulated like this. Yeah, you can define it, but there are some tiny, but let me mention is that once we can do it on disk, nothing can stop us from doing exactly the same thing on any surface of any genus, with any number of holes, and so on. We can play exactly the same game, so we can get this, some space for any graph and so on. That's one thing. Yes. Sorry?
If I take a fixed graph and fixed edge weights, and flexibility depend on orientation, perfect orientation.
Of the graph. Yeah. Yes, I think so, but that's kind of non-trivial way. So, but right now, just keep things simple. I want to actually fix geodesics. That will be my choice. But let me tell you, like maybe I have a few minutes left. Let me give you the second half of the talk in 1 minute, because really I didn't tell you like the main result yet. But let me tell you the main result, where all this comes from. Let me go back to this inequality. So all this kind of, we have this space that satisfies this inequality, which is kind of, and so this is certain cone of dimension n squared. But it's polypositroids are a special case of polymatroids that satisfy much larger dimensional cone. So we have this n squared dimensional cone, which maps into 2 to the n dimensional cone. But it maps in a non-trivial way. It kind of has a given by piecewise linear map. And so basically it's kind of broken into different pieces, which are given by different, tropical Playback graphs. And every piece kind of embeds into some linearly. But there will be, so somehow we have actually, you talk about not a positroid cone, but these things is subdivided into much smaller pieces. and each piece is embedded linearly. So how do we describe these pieces? There is a very simple explicit description of these pieces. And okay, and there is a formula that I don't want to, because since we are kind of closing to the time. So there's an explicit formula, which is kind of, to make it short, it's given by, that's the main thing, kind of technical, and this embedding of this thing into submodel, into that thing, into submodel cone, is given by tropical determinant of matrix. So you have to look at the okay. Let me, if I have 5 minutes, let me write down one formula that kind of basically implies many things. That's so want to go figure out how to go from this thing that satisfies these inequalities into the cone, submodular cone that satisfies those inequalities. Okay, so how to go from Rij, which has some very special ranks, to arbitrary ranks. So we already know some of them. If this I happen to be a cyclic interval, that's exactly Rij's. But not all subsets are cyclic intervals. We need to figure out what should we do with other subsets. And so theorem is that, let me write down any subset as a union of cyclic intervals, like A1, B1 minus 1, union A2, B2 minus 1, and so on. AL, BL minus 1. Then, of course, the rank of I should be like at most rank of this plus rank of this plus rank of this, but it can be smaller. So theorem is that, so it means that 1, so R of I equals to the minimum overall ways to match A's and B's. So overall permutations, W from A to B, are all matchings of sum of ranks A, like over all little I in rank of I, comma, W of I. And you can realize this. That's exactly tropicalization of the determinant. Let me write it right, please. That's the tropical determinant, the indices, subsets A and B of the matrix R. So R is n by n matrix. You have these two subsets, A and B, and you take tropical determinants, and that's exactly how you embed one thing into the other. So notice that here we have some overall like L factorial terms. But actually, notice that, so we have like some, let me say, we have some A's and B's, like maybe we have source, sink, source, sink, source, sink. We have to some overall ways to match black dots with white dots, overall possible choices. Yeah, maybe something like this. That's the kind of standard one. There will be like L factorial, but not all of them are going to be actually important for us. So we will never, if we have at least one crossing in our matching, right? So if we kind of match one dot to the opposite, say in this example, so then we can replace this pair of chords by this pair of chords, and we get something smaller. So in this minimum, instead of summing over L factorial things, we have to sum over Catalan things, only over non-crossing matchings. And that actually, this condition kind of really simplifies things. And the other thing, notice that here in this theorem, we only appear like what we have these minors for A and B's which are interlaced on a circle, because these like A and B's are interlaced. But actually, another simple lemma that if we have this non-crossing condition, so once we can express any A and B, like any pair of subsets, which not necessarily interlace, in turn as a sum of interlaced ones. Again, very easy. So if you have some diagrams, any subsets, two pairs of subsets A and B, can be expressed as a sum of interlaced things. It breaks into connected components. So really, this information tells you information not only about these kind of interlaced tropical minors, but about all tropical minors. That's equivalent. So let me kind of just maybe make one summary. So basically, yeah. Yeah.
So this is one function that
That's one function that comes. So we kind of single about among all submodular functions, we're telling which one are polypositroids. So polypositroids are exactly those submodular functions which are obtained by tropical minors. So let me kind of just maybe use 1 extra minute, write down that this fan, let me say polypositroid fan, PPN, is basically the same thing as tropical. So here we have like n by n matrix, all minors of n by n matrix. That's actually tropical GLN, tropicalization of the positive part of GLN. Well, to be more precise, we have to mod out by torus, which is the same as, let me put tropical in quotes. GLN can be embedded into the tropical Grassmannian GRN to n, again, modulo torus, again, positive part. Okay, now I put in the quotes because notion of tropicalization depends on the choice of coordinates. So really, tropicalization, it should be tropicalization of Grassmannian, but tropicalization of coordinatization of Grassmannian. So Lauren, Williams, and David wrote a paper about tropical positive Grassmannian. What they did in the paper, they should be more properly called tropicalization of parameterization of Lebesgue parameterization of the Grassmannian. So there's one particularly nice parameterization. So here, we're actually parameterizing Grassmannian in a more naive way. We're actually parameterizing it in a coordinate chart. So it means that it's, again, this tropicalization quote, we're parameterizing coordinate parameterization of the positive Grassmannian in one particular coordinate chart. So somehow, and since coordinate chart does not see the whole Grassmannian, we will be missing some cells. So this is not literally whole tropical positive Grassmannian, but it's like some kind of coordinate piece, like a coordinate affine subspace inside of a positive Grassmannian. So that's kind of just, but I should mention here that, like many different things, that's can be said the positive part of the Newton polytope of the product of all minors AB of a matrix. So that's also appeared in some talks. I should say other words like triangulations of the product of simplices, tropical hyperplane arrangements, and so on. So basically, this theorem, this object can be kind of understood in many different ways. But the key word here is we're not considering this whole thing, but we're considering kind of non-crossing things. Like this non-crossing condition is equivalent to this positivity condition. So, but anyway, so there are many different kind of languages in which you can formulate this theorem, but maybe I should stop here. So thank you very much.
Any questions for Alex?
What's the dimension of the subspace of the cone of submodular function that corresponds to the poly?
Because, okay, this poly-positroid is given by this matrix Rij, which is n by n matrix, except that you require that I on the diagonal you have 0. So it's n square minus n. So it's n square minus n inside of this 2 to the n minus 2, if you like, dimensional space.
Yes.
So a small question. Do those polypositroid polymorphs decompose naturally?
So I didn't hear
Oh, sorry. Do those polypositroid polymorphs
Do they, I get it.
do they decompose in a nice way at all?
Yeah, what?
They decompose in a nice way.
Oh, decompose. Ah, like Minkowski sums? That's a good question. So if you look at this thing here, oh, actually, I forgot to write it. It's product of all minors. So because it's of product of all minors of a matrix. So if you look at this thing here, then this whole thing is actually Minkowski sum. Actually, that might be relevant because Nemo likes to decompose things. So this is Minkowski sum of many Birkhoff polytopes. So because Newton polytope of a determinant is Birkhoff polytope. It's a Minkowski sum of, Birkhoff polytopes for all choices of A and B. But that means that this whole thing decomposes, but we are looking not at all things, but at the positive part. So somehow it is certain subset of a bigger polytope, certain kind of open piece of a bigger polytope, which is Minkowski. So let me formulate it like this. It's a subset of the normal fan of certain things that decomposes into Minkowski sum into Birkhoff polytopes. So in this way, it kind of decomposes into Minkowski sum. Yeah. Yeah.
Positroids also lend themselves to like polypositroid stratification somehow. In a way, like positroids lend themselves to.
Okay, that's a good question, right? We can think about this space of subspaces, and we can stratify them by polypositroids. Yeah, will be certainly interesting. I don't know. Yeah, there is that we can define it in exactly the same way. That would be interesting to study. Yeah, yeah. So there should be some kind of polypositroid stratification of the configuration of subspaces, of the positive configuration of subspaces. But again, these things is a little bit tricky because, as I said, in order to figure out when given configuration of subspaces is positive is actually kind of a non-trivial verification. Yeah.
So another way of thinking about positroids is that they are the oriented matrix where the orientation is positive.
Yeah.
Do you know if there's a theory of oriented polymatrix where a statement like this could be true?
Yeah, that's. Yeah, I don't. Probably, maybe. I don't know. I'm not such an expert. Well, maybe we should ask Bernd. Is there a notion of oriented polymatroids?
That somebody has written it.
Yeah, there should be.
Are you going to write a paper about it next week?
Yeah.
I mean, it feels like
That seems
whoever
like
they
an
would be in this
natural
room,
thing,
yeah.
so maybe. Yeah, there should be. Yeah,
Should be a paper.
But I don't know if anybody did that.
Yeah.
That fan of polypositroids, how can you read of the cone structure of these?
Okay, cone structure again. That's exactly this theorem. Structure is given by fixing for any A and B. You have to fix which term in this minimum is we take. So for any A and B, you need to fix a matching between A and B for all choices. Again, this cannot be just an arbitrary matching. They should, first of all, it should be non-crossing, but it should satisfy also some additional axioms. For example, there's something called linkage axiom. So it satisfies some additional axioms or some compatibility condition, but basically this data, choice of all matchings between all A and B, uniquely determines. So there are like several combinatorial description of this. You can describe it either in terms of this matching, I call them matching ensembles, or in terms of these tropical Pletbeck graphs. That's another combinatorial data that describe these cells in the way how. Another thing we can describe it in terms of triangulation by giving some collection of non-crossing trees and so on. So there are many different languages in which you can describe these pieces combinatorially.
Okay. Just wondered, do you have a good way to get a handle on the faces of the Newton polytope or the facets?
Okay, that's a very good question. And in order to do the matchings, like if you, so it means that now if we're to care about faces, there might be several matchings, kind of. So right now, like the open strata are exactly given by the collection of matchings. if you want to talk about high-dimensional phases, you need to, instead of matchings, a more convenient language is the language of polyhedral subdivisions. It will be positive polyhedral subdivisions of the product of two simplices. So people study polyhedral subdivision or triangulations, and more generally polyhedral subdivisions of products of two simplices. It is a little kind of positive part of this. We have this kind of additional non-crossing condition. So, but that's kind of so to say non-crossing polyhedral subdivisions of products of two simplices. That's one way to describe them. But another way is in this language of tropical Plebbe graphs. Yeah.
More of a comment rather than a question. Comment about how these things could show up in nature. Of course, this last thing you were talking about the possible connection with surface is very interesting. But the sort of more simple way that matroids show up in physics is when you compute Feynman integrals as loop integrals over loop momenta. Mm-hmm. And the vector of the configuration vector of the matroid is sort of the momentum that flows through an edge. Mm-hmm. So it feels that the way that maybe not a poly-positroid, but a polymatroid could show up in physics is if for some reason you wanted to have graphs where each edge carries an entire vector space rather than just a single momentum, and you want to integrate over them. So maybe it's the kind of things that Nick likes a lot. Regionalize graphs in this way.
Yeah, that sounds
comment.
Yeah, definitely sounds.
So these are special matching fields that you get for one basis. You can fixing a basis, right?
Yeah.
If you take if you look at arbitrary matching fields, is there a notion of positivity? Notion of positivity for general matching.
That's a good question. There should be, but again, yeah. So there should be, but so in general, but somehow what I'm trying to say is in this thing where positivity means exactly non-crossing conditions. All matching should be, if you draw them by chords in the circle, they should be non-crossing. That's kind of combinatorial counterpart of positivity in this picture. But yeah, but there should be more kind of general concept of positive matching. And I should also mention we can generalize these things. So far we are kind of we can generalize it to root polytopes, which are some collection of roots, any collection of roots. Right now we are talking about like full root polytopes, where we take all positive roots. But there is a special subclass of root polytopes that appeared in one of the talks. If you, under the name of H polytopes, you can do similar things for any H polytope. But again, kind of bipartite case is kind of trivial because in bipartite case graph, if like all sources are on the left, all sources on the link, there is only one way to connect them by non-crossing matching. Somehow bipartite case, for this positive part of the bipartite case kind of becomes trivial, but interesting things appear if kind of sources and things are interlaced. Then there are many kind of more interesting. Yeah.
Yes. Is the realization space of this polypositroid is 4?
Is what?
4? The realization.
Oh, good question. Yeah, I don't know. Well, that's probably Pasha can prove it or somebody else. Yeah.
Can you repeat the question?
Is it a ball? It's like for the realization space of polymatroid due to Lars and Thomas and Steven is a ball. So natural to assume that
it should also be a ball, but yeah. So we don't know yet.
It's initial conjecture.
Any other questions for Alex? All right, now let's thank him again for a wonderful talk.